Welcome back. In this video, I'm going to show how to use regular expressions to specify different aspects of programming languages. Let's begin with the keywords. And this is a relatively simple case, and I'll just do it for 3 keywords. I'll write a regular expression for if, else, or then, and it'll be obvious how to do it for more. So let's write a regular expression for if, and that would be the regular expression for I, and followed by the regular expression for f, and we're taking the concatenation of these two. And then we're going to union that with the regular expression for else. And what is that? Well, else consists of 4 individual characters, so we have to write out the concatenation of those 4 characters. And as you can see, this is a little bit verbose with all of these quotes and kind of messy to read. So in fact, there's a shorthand that's normally used, and let me switch over to that right now. So if I want to write the regular expression for a sequence of single character expressions, I could just put quotes around the outermost characters in the sequence. So for example, most of the tools will let you write this. I put a quote at the beginning, I write IF, and then I write close quote, and this means exactly the same thing as this. This is the concatenation of 2 single character regular expressions. And similarly for else, and similarly for then. And if I have more keywords, I just write them out and union them all together. Now let's consider a slightly more complicated example. Let's think about how to specify the integers, which we want to be the non-empty strings of digits. So the first problem here is to write out what a digit is, and that's pretty straightforward. A digit is just any of the individual characters 0 through 9, and we already know how to write out single character regular expressions, and it's just a union of 10 of those to specify this. And it'll take me just a moment to finish. There we go. So that's a regular expression for the set of strings corresponding to all the single digits. And because we'll want to refer to this from time to time, and also because that's a very common thing to want to do, most tools have a facility for naming regular expressions. So for example, I can name this one to be digit. So a single digit is anything that is generated or is in the set denoted by this regular expression. And now what we want to do is to have multiple digits. Well, we know a way to do that. We can just iterate a single digit as many times as we like, and so here we get all strings, all possible strings of digits. And this is very, very close to what we wanted, except that the string that we want has to be non-empty. We don't want to count the empty string as an integer. And there's an easy way to do that. We just say that the whole sequence has to begin with a single digit, and then it's followed by 0 or more additional digits. So just to reiterate that, we say there has to be at least 1 digit, and then it's followed by 0 more additional digits. And this pattern, actually, for a given language, is extremely common. So if I want to say that I have at least 1 A, I write that as A star, because this says 0 or more A's, the second part says 0 or more A's, and the first part says there has to be at least 1 A. And because this is so common, there's a shorthand for it. I think it's supported by every regular expression processor, and that is to write A+. And A+ means is just a shorthand for A star. And so we can actually simplify this regular expression a bit and write simply digit plus. Now let's look at yet another example, even more sophisticated than the previous two. Let's think about how to define the identifiers, which are strings of letters or digits that begin with a letter. And so we already know how to do digits, so let's focus on the letters for a moment. So how will we write out a regular expression for the letters? Well, we're going to want to name it, so we'll say that the letters are actually a single letter. And now we have to write a regular expression for all the individual letters. And that's straightforward but tedious. We have to say little a, lowercase b, lowercase c, lowercase d, and well, as you can see, this is going to be rather a large regular expression. We're going to have 26 lowercase letters and 26 uppercase letters, and the whole thing is going to be rather tedious to write down, so let's actually not do that. Instead, let me mention a shorthand that the tools support to make it easier to write out exactly this kind of regular expression, which is called a character range. So inside of square brackets, I can write a range of characters. So how do I do that? Well, I have a starting character and an ending character, and I separate them by a hyphen. And what this means is the union of all the single character regular expressions beginning with the first character and ending with the second character, so everything in between. So this is exactly the regular expression for all the lowercase letters. And then I can have another character range inside the same square brackets for all the uppercase letters, so capital A through capital Z. Okay, and this regular expression here on the right defines exactly the big union that I didn't want to write out. Okay, and that gives us a definition of a single letter. And now we're in great shape. We already have a definition for a digit. Now we have a definition for letter, and so that we can write out the rest of this definition. So we want the whole regular expression to always begin with a letter. Okay, so an identifier always begins with a letter. And after that, it's allowed to be a string of letters or digits. Okay, so the or suggests that there's going to be a union. So after the first letter, we can have either a letter or a digit. And then we can have an arbitrary string of those things. So we put a star on the whole thing, and that is the definition of an identifier. It begins with a single letter, and it's followed by 0 or more letters and digits. Now, because we're doing a complete lexical specification, we also have to deal with even the parts of the string that we're not really interested in. We have to have at least a specification of them so that we can recognize them and throw them away. In particular, we have to be able to recognize the white space. And we're going to just take white space to be a non-empty sequence of blanks, new lines, and tabs, even though there are other kinds of white space characters, things maybe like rub out. Depending on your keyboard, there might be others, but these three will suffice to illustrate all the important points. So, a blank is relatively easy to write down. That's just single quotes around a blank space. But there's a problem with new line and tab, because a new line, a carriage return in the file, has special meaning. Typically, you end the line, you end whatever command you're working on in these regular expression tools, lexical tools. And tab also is not an easy thing to write down, and it doesn't look much different from a blank in a lot of cases. So what tools do is they provide a separate name for these, and typically it's done by having some kind of escape character, and a backslash is the most common one that's used, and then followed by a name for the character. And so backslash n is typically used for new line, and backslash t is typically used for tab. And I just want to stress, the reason for doing this example is to illustrate this, that we have to have a way of naming some characters that don't really have a very nice print representation. There are other characters that don't even have really any kind of print representation, and we still need a way to talk about them in our regular expressions because they might be embedded in a file that we have to lexically analyze at some point. And so anyway, the way this is done is by providing a separate naming scheme for such unprintable characters. And typically that's done with an escape sequence, so something beginning with a special character like backslash, followed by the name of the character, so N for new line in this case, and T for tab. And so to finish off our definition, this gives us one character white space, and then we want a non-empty sequence of such things, so we wrap the whole union there in parentheses and put a plus on it, and that gets us what we want. Let's pause for a moment in discussing programming languages and look at another example of using regular expressions from a different domain. Here I have an email address, and as it turns out, email addresses form a regular language, and every email processing device in the world, so your mailer and the mail servers that you use, all do regular expression processing to understand what the email address is telling them in the email messages that go by. And so we can think of an email address as consisting of 4 different strings separated by punctuation. There's a username and then 3 parts to the domain. Okay, and let's just assume for simplicity that these strings only consist of letters. In practice, they can consist of other kinds of characters too, but let's just keep things simple. And we can write out the more complicated thing using regular expressions, but the structure will be the same as if we just consider them to be made of letters. And then these four strings are separated by punctuation. So there's the @ sign and 2 decimal points that form the separators of the strings. And so this is a relatively straightforward thing to write a regular expression for, given what we know so far. So the username would be a non-empty sequence of letters, and then that would be followed by an @ sign. And then the first part of the domain would also be a non-empty sequence of letters, followed by a dot, and then the rest is just the same. Okay, so over here, very quite concisely, we have specified a large family of email addresses. As I said, in reality, the email addresses are slightly more complicated, but they can be written out with just a slightly more complicated regular expression. Finally, for our last example, let's look at a fragment of the lexical specification of a real programming language. In this case, that language is Pascal, which is in the Algol family of languages. Pascal is an early example of a typed language, and it's in the same general family as Fortran and C. And this particular fragment of Pascal deals with the definition of numbers. And so let's take a look here. I'll start at the bottom and look at what the overall definition of a number is. So a number consists of three things: some digits, and I'll just read out this abbreviation: an optional fraction and an optional exponent. So we're dealing here with floating point numbers. And so a floating point number can have a bunch of digits, and then it can be followed possibly by a fraction or not, and that can be followed possibly by an exponent or not. And the idea, although we can't see it just from this particular definition, is that either the fraction or the exponent can be present independent of the other. So now let's work briefly from the bottom up. Let's just check that digits are what we expect. So a single digit is in fact the union of all the common digits, just as we would hope. And then a non-empty sequence of digits is digit plus. So this is what we've already seen. And now the interesting bit is to look at how the optional fraction and the optional exponent are defined. And the optional fraction looks a little less scary, so let's do that one first. So what's going on inside the fraction? Well, if we have a decimal fraction, there's going to be a decimal point, and that's going to be followed by a string of digits. So this is just the fractional part of the floating point number. It's the stuff that comes after the decimal point. And what's this plus epsilon doing out here? Well, remember, the plus is union, and epsilon stands for the empty string. So what this is saying is that either the fractional portion of the number is present or it's completely absent. So this is how you say something is optional. You write out the regular expression for the thing, and then you do plus epsilon at the end, and that means, well, either everything I said before can be there or nothing is there. Okay? And the optional exponent is structured similarly, but is somewhat more complex. So you can see that the whole exponent is optional because there's some regular expression here that's unioned with epsilon. And so either something is there, and this is the optional, this is the exponent part, or it's not present at all. And now let's look inside how the exponent is defined if it's there. So an exponent always begins with e. So this is exponent, standard exponent notation. And it always has a non-empty string of digits. So there's e followed by some digits, and in between, there's an optional sign. We know the sign is optional because epsilon is one of the possibilities. The whole sign might be absent. And then what are the possibilities for the sign? Well, it could be negative or it could be positive. So either there's a positive or negative sign or no sign, in which case, presumably, it's interpreted to be positive. Now, this idiom, where we have plus epsilon to indicate that something is optional, is also extremely common. And so there's another shorthand that many tools provide. So another way of writing this that's common is to say that that's my fractional component, and then it might be absent. So the question mark after a regular expression just means exactly this construction, that we take that regular expression and we OR it with epsilon. And so this one, this regular expression, is a little more complicated. It has two optional components. So let's just write out what that would look like. So we would have the exponent begins with e, and then we have a sign, which is either plus or minus. And that's optional, so we put a question mark after it, followed by a non-empty string or digits, and then this whole thing is optional. The whole exponent is optional. So this is an alternative and more compact way to write this expression. To wrap up, I hope I've convinced you in this video that regular expressions can describe many useful languages. We've seen some fragments from programming languages, but also we saw that email addresses could be specified this way. Other things that are regular languages are things like phone numbers and file names are also regular. And there are many, many other examples in everyday life where regular languages are used to describe some simple set of strings. And I also want to emphasize that so far we've used regular languages as a language specification. We used it to define the set of strings we're interested in, but we haven't said anything about how to actually implement lexical analysis. We still need an implementation. And that's what we'll talk about in future videos. In particular, we're going to look at the problem of given a string S and a regular expression R, how do we know whether that string is in the language of the regular expression R?